So I'm Kritika Jain. So yeah, currently I'm working as a postdoc research associate under National Quantum Mission in Professor Rejish Nath Group in IISER Pune. But today I'll be talking about my previous work, which has been carried out in Okinawa Institute of Science and Technology under Professor Thomas Bush. So yeah, I'll be talking about how nanofiber waveguides can be used for quantum technologies. Uh, First, let me introduce what is optical nanofiber. So, conventional nanofiber is well known, which has a core and cladding in the microns, and experimentally it can be tapered using stretching and heating. And the waste region is called nanofiber, which has a core in the nanometer size, and vacuum acts as a cladding here. Due to this small diameter, uh, the optical mode of the light that extends outside the fiber, which is called evanescent field, and this evanescent field is exponentially decaying outside the fiber. Uh, and the conventional fiber has a very low refractive index contrast. That's why it is called weakly guiding, while optical nanofibers has a very high contrast between core and cladding because vacuum is a cladding here and it provides a strong optical confinement. And we can interface atoms in this evanescent field, which the combined system gives us a significant role in quantum optical technologies. So first, I'll briefly explain how a single emitter couples to the nanofiber. So if an emitter is placed in the evanescent field of the optical nanofiber, it has two channels to decay into. First is in the guided modes of the fiber with the decay rate gamma 1D, and uh, second channel is into the free space, which is like with the decay rate gamma radiation. So, and gamma total is the sum uh, of both these channels. So, I want to note here that if an atom is in free space, it is decaying with the decay rate gamma 0, which is not equal to gamma total because of the modified optical states due to Purcell effect. So here are few uh, parameters which can be used to quantify this coupling. And in this talk, I'll be more focusing on coupling efficiency, which can tell us how much of the light is guided into the waveguide or nanofiber with respect to the total light. And I'll also show some results on Purcell factor, which is the total density of optical states increased due to the presence of nanofiber with respect to the free space. So yeah, here I am showing some nanofiber based implementations. So nanofiber, it provides a platform to trap the atoms around the fiber using two counter propagating light. We can create the optical lattice around it and can trap the atoms. And this after these atoms are trapped, they give a light matter interface and which can be used for efficient photon channeling. And this light matter coupling depends upon the radius of the fiber, as you can see here, and also the distance between the fiber and the emitters. And uh, these guided modes can also mediate long range atom atom interaction when the atoms are not talking to each other directly but through the nanofiber. And this can be used to create long range entanglement also, which I will show you later. And this has nanofibers have also been used for efficient storage in EIT based quantum memories and also efficient retrieval in one direction. So my motivation here is to improve this whole light matter interaction platform uh, of emitters interface with nanofibers for enhanced quantum control and photon coupling. So the single nanofiber has been already studied and well understood. So my proposal here is to study two nanofibers. When the atom is trapped or placed between two nanofibers, um, we can increase the efficiency significantly. And so this coupling of guided modes between two parallel nanofibers was already studied in the group by Family Keen and others. But my problem is to study the whole radiation dynamics of the system. And as radiation modes are infinite in number, it is difficult to calculate the coupling of infinite radiation modes by standard eigenfunction method. So that's why I use the Green's function approach in my problem. So I'll not go into the details of every mathematical equation, but I'll give the physical meaning of these. So we start with the electromagnetic wave equations for a point source, uh, which give us the Green's function for electric and magnetic Green's function. So it basically tells us how the electromagnetic field at a point R propagates to the point R dash in the space. So to simplify the problem for our symmetry, for our geometry, I take the Fourier transform in the z coordinate, which is the along the fiber axis, which give me this equation, and simplify my problem from 3D to 2D. And later I'll take the integral to convert it back to 3D Green's function. So here is the full calculation of Green's function. So here this method is valid for any number of fibers. So in this picture, I am drawing the three fibers, and I exploit the cylindrical symmetry of the system. And this boundary is imaginary boundary here. So I can write the field in two ways. One is the local field expansion, which can be written around each cylinder using Rayleigh multiple method, and the field can be written as a sum of convergent and divergent field in the form of Bessel and Henkel functions. And the other way to write it using Green's second theorem, which is valid at any point in the space, and it is the sum of the field coming from the source and the field coming from scattered from all the cylinders. So these both should be valid in this annulus around each cylinder. So we can equate them, and we get this Rayleigh identity. And this gives us the relation between these scattering coefficients A and B. So the goal is to calculate all these scattering coefficients, so that using them we can calculate the Green's function. So one relation we have this Rayleigh identity, and the another relation we can get using boundary conditions of the nanofibers. So R is the reflection matrix here, and this is the matrix form, and using combining these two identities, we get this final equation. And all the right hand sides are known now. So we can calculate all the scattering coefficients B, and using B we can calculate this Fourier transformed Green's function, and then doing the Fourier integral with respect to beta, which is the propagation constant along the z-axis. We can calculate the z component of the Green's function, and using this, we can calculate the transverse component of full 3D Green's function. So, and using these Green's function elements, we calculate the physical quantities in our system, which is the decay rates. So, gamma is the total decay rate, which is given by the imaginary Green's function elements, and gamma 1D is the guided part of the decay rate, and delta omega gives us the lamp shift, which is given by real part of the Green's function. So using this gamma and gamma 1D, we can calculate our coupling efficiency. So now we have this formalism in hand. Now we move to the results for a single emitter trapped between two parallel nanofibers. So the main result is maximum coupling efficiency can go up to 54% for touching fibers compared to 30% in single nanofiber. And also maximum Purcell enhancement can go up to 10, factor of 10. So in this panel B, we scan the coupling efficiency with fiber separation, that is D, between the fibers and the fiber radius. So as we go far away from the fiber, coupling efficiency decrease, but as we increase the radius, we found this optimal radius where the efficiency was maximum around here 175 nanometer, and the maximum efficiency is around 54%. And similarly, we found the efficient high Purcell factor of 10 when the fiber separation is very small. And in D, I vary the transverse position of the emitter to see the robustness of the emitter position between the two fibers, and we see the efficiency remains high at most of the points. So this shows the robustness to the emitter position. And here in E, I fix the radius of one fiber and vary the radius of second fiber. So the efficiency is maximum for identical fibers here, and but within few plus minus nanometer also the efficiency remain above 50%. So this also shows the robustness to differences in fiber radii. And here in F, I plotted the lamp shifts. So we found these few blue curved sites where the lamp shifts was 0. So we believe that these sites can be exploited in the quantum metrology applications where we want the lamp shifts to be 0. So now I move to the two atoms and see can we create the entanglement using using the nanofiber system. So I evolved the master equation, standard master equation with a driving omega, and this coherent and incoherent coupling between the atoms, they are given by the Green's function elements. So concurrence is a measure of entanglement, and I calculate the concurrence here to quantify entanglement. So here are the results for two emitters. So here I plot the concurrence with the vary with the driving frequency and coupling efficiency. So we found the maximum concurrence for high efficiency and moderate driving. And the interesting thing here is for a fixed driving, there is a cutoff in coupling efficiency below which we find the concurrence is 0 and above which it is finite. So which I'm showing here as a transient concurrence. So this blue curve shows the N is fiber here, number of fiber. So for one fiber, there is a sudden death of entanglement in finite time, while for two fibers, it is transient entanglement has a peak, and also it persists for longer time. This two fiber system can be used to create efficient entanglement between two atoms which are far from each other. And now I extend this work to more atoms, n atoms, and write the effective non-Hermitian Hamiltonian. So here also this incoherent and coherent interaction terms are given by Green's function elements, and we get the n cross n matrix. And by diagonalizing this effective Hamiltonian, we find the collective modes, where real part is collective frequency shifts and imaginary part is collective decay rates. So we find the super radiant and subradiant peaks. So here is for one fiber and this is for two fiber. So these simulations were done for 100 emitters between the fibers. So this shows the decay rates as a function of lattice constant, and I am highlighting here the most super radiant and subradiant peaks. So two fibers shows us more pronounced super radiant and subradiance, and here I am showing the scaling for these uh, peaks. So as we increase the number of atoms, for one fiber they increase, but for two fibers they are more pronounced. And here in super radiant peaks, even this slope is increasing for the two fibers as we increase the number of atoms. We can use this two fiber system to create subradiant modes, which can be exploited for quantum memories later. And here I'm showing, so until now I showed the results for linearly polarized emitter. So here I take the circular polarized emitter. So whenever the circularly polarized emitter is near the nanofiber, it preferentially emits into one direction, right or left. This is well known for single nanofiber because of the local polarization of light is elliptical due to the longitudinal field component in the nanofiber, so which gives us chiral emission. So here I am using two fibers to control this chiral emission continuously. So if we move the atom from emitter X position from here to here, we can see we can tune the direction and even the magnitude into the right and left direction. So here directionality plus means it is going into the right direction, while negative means it is going into the left direction. And at the center, we can switch off this directionality also according to our need. While for one nanofiber, it is only one directional always. So it can be used in on-demand photon routing. So here is the summary of my talk. So I designed and implemented a full computational model based on 3D Green's tensor, which integrates Rayleigh multipole methods and Fourier integral, and to calculate dipole-dipole interaction within two nanofiber system, and use that to show significant enhancements in photon coupling efficiency and Purcell factors, and to establish long-range atom-atom entanglement and also showed pronounced superradiance and subradiance effects, where subradiant or long-lived states can be exploited for quantum memories. And this also demonstrated controllable chiral emission via emitter positioning, which may be highly relevant for photon routing in quantum networks or quantum communication. So here are my collaborators. So this is Thomas Bush group when I was there, and Thomas Bush, family Keen, and Louis Rooks. And these students did some later simulations, Ilya from Russia and a version from IISER Pune. Thank you for your attention.
Thank you very much for this interesting talk. We have time for questions. Anna Maria?
Very nice talk. I have one question. When you talk about the single emitter, the single atom, you talk about a line shift that is zero. Can you remind me what is the definition that you're using for the line shift? For me, sometimes it's more like the density shift from dipole-dipole interactions from the other atoms.
Lamb shift?
Yes.
So that is the scattered part only. So with respect to the vacuum, it is shifted due to the nanofiber.
Okay, that's the static part of the green function.
Yeah.
Okay. And my second very brief question is, what is the progress for experimental implementation of this system?
Yeah, that is the difficult part, but I have added one slide for that. So this is the motivation in the chip. People have done this. You can make the parallel nanofibers by bending them, and they have shown this strain sensor. So so in the experiments also, I think you can bend like this and you can make parallel nanofibers. Yeah,
I was going to ask a similar question about what are the challenges to trapping an atom? Because there must be a very strong Casimir polar potential when you put the two fibers this close together.
Two fibers, it will be.
Distort the trapping potential, but
I think so, but when an atom is trapped near a nanofiber, it's around, I think, 200 nanometers. And if we put another fiber, so it's like 400 nanometers. So in that region, with respect to the size of the atom, maybe they are less, but they need to be taken account, and I didn't.
Any final questions? So normally I would thank all the speakers in the session, but I think two of them won't hear. So let's thank the final speaker. Thank you.